All right, so we're going to pick up in section 2.1 with numeration systems, and the last numeration system we had talked about was the Romans. We had written down kind of some of these details about their numbers specifically, and then we were on our way to talk about a couple of different features that are present in their number system. One is a subtractive feature that keeps us from writing a numeral a bunch of times to represent a number, like the 4 ones that's on Ray, the example. And so it shouldn't be 4 ones, right? It should be an I and then a B. And the other one is a multiplicative feature, which is going to allow us to write numbers that are bigger than, say, 1,000. Right? Because what if you have the desire to write the number 50,000? There's got to be a better way than writing 50 of the M's, right? So that's what that's going to deal with it for us. So, all right. So the first property, the subtractive property, you know some of this. So. When you're repeating, they will never use a symbol to repeat itself more than 3 times. So if you have the number specifically 4 or 9 in one of our numbers, and you're wanting to deal with their number system, we would never write 4 ones or 4 L's or 4 anything, okay? We would always find a way to write it with fewer values. So specifically, if you had the number 4, as we've talked about, you would write it as IB. When a number, basically the way you identify from their number system when that's happened is that they have a smaller numeral in front of a larger one. So the I before the B is awkward because 1 is smaller than 5. And in the other case, we actually see the number written the other way around. The bigger value would be listed first. Okay? So when you see a smaller value in front of a larger value, you've got a subtractive feature going on. In particular, this applies, like I said, to 9s and 4s. So if we wanted to write 90, you take a look back over here. I don't want to write 9 10s. I also don't want to write a 50, an L, right? And then 4 10s, because that's 4 of the same symbol. We're not going to write 4 of the same symbol. So what could I do with these symbols in here instead to represent the number 90? XC. That's exactly right. Now, so this is XC. Now, 99, you might be awfully tempted to say, looking at 99, what would it be nice to do? It would be great if we could do IC, wouldn't it? They would never have written IC that direction because that's just not appropriate for their system. They would always use one value less than what they were on. So for instance, the number C, right here, this 100, the only value that you would ever see in front of a C is a 10. One place value less, okay? The only value you would ever see in front of a 50 is a 10 because it's one value in that same place instead of less. So we're going to treat the 99, in other words, as though this was 90 and then 9 more. That's kind of how you're going to think about it, okay? So we know how to get 90 because we just did it. How do you get 90? XC. And then how do you get 9? IX. That's probably something you've seen before. It's a small enough digit. So this IX, right? So here's the I and then the X. So in other words, these are sort of grouped together in the following ways, right? You have some overlap here and the overlap here. The only numbers that you would see associated with an M or a D in front of it would be a C. The only number that you would ever see associated with the L or the C in front of it would be an X. Right, so let's use that one since you gave me some examples. You had 49. Oops. Well, yeah. We're going to treat it. The number 49 is 40 plus 9. So if you did the number 40, how would we get the number 40? XL. And then how would you get the number 9? IX. So it may not be what we really want it to be, but that's really not the point. The point is that we want to do it the way that they would have thought of it. Okay? All right, so that's the whole issue of the subtractive feature that you see going on with theirs. The multiplicative feature, what's it doing today? The multiplicative feature has this idea of being able to write a bar on top of something. So kind of like back in when you were doing, like repeated decimals, when you put a bar on top of something, it's like that kind of a bar. Okay? Okay? So when you're doing something that's multiplication, if you have a single bar on top of something, it means multiply by 1,000. And if you have a double bar on top of something, it means multiply by 1 million. Okay? Everybody good so far? Yep. So when you see this number 9,000 here, you literally want to think of this as 9 times 1,000. We'll write the symbol for the 9 down, and then we'll put a bar on top of it to represent the times 1,000. So this is the third time now that we've done the symbol for 9.
IX.
It's IX. Yes, it is. And then a bar on top of it's going to be 9,000. It's going to be 1,000. All good? Okay. If I put 2 bars on top of this, the same value, what would it be? 9 million. Good. All right, so let's actually do one without me. I don't know why it's not letting me switch today, but. All right, we're going to consider the value MCMX. Just like last time, our concern is what's the next number, what's the previous number. Now, if you want to turn that into our number to think about it, you can. But you don't have to. That's really not what we're trying to get at. We're trying to get at, pretend like I'm a Roman, and you owe me MCMX numbers of dollars, and you borrow $1 more. Now, how much do you owe me? Are you with me? All right, so there's the number before, and there's the number after. I think probably doing the number after is the easiest on this one, so let's tackle that one first. So part B, what Roman numeral comes after MCMX? Right. MCMXI. Right? It's just one more. It's number 1 at the end. Okay. Now, if you want to do the number that's 1 before, we would look at our last digit. It's an X, which represents what number? 10. And the number in front of it's not smaller than 10, right? Right? So it really is like having 10 at the end. So if you have 10 and you want to take 1 away, we turn into the number 9. So I can write the MCM, right, as it is, and I want to turn the 10 into a 9. How do I write the digit 9? IX. All right, so now let's actually do part C, which is turning this into a Roman numeral. All right, so going back up to what we had before, what number is M? 1,000. So let's just identify the numbers we have here. This is 1,000. What's C? It's what? Just what's C itself? Final C. C is 100, and M is 1,000. So you've got a smaller number in front of a larger one. So the 100 in front of 1,000 means the 100 and 1,000 becomes the number 900. Okay, so this piece right here is 900. And we already said the X is 10. So what number is this? 1,910. Well, that could be a year, right? The year 1910, that would be a possibility. Okay, we're going to go the other direction on this one too. We're going to do 1,492,019. And we're going to turn it into a numeral. So when you're thinking about these numbers, or this number specifically, it's a rather large number, correct? And you can kind of think about the way that we separate our commas with things being very convenient for the Roman numerals. Because there's the millions, and we have the things that are in the thousands, and then we have the other digits that are small enough to be represented by Roman numerals specifically. Okay? So we're going to sort of represent these in 3 separate stages. First, how do I represent the number 1? Because it says 1 million, right? How do we do the number 1? I. How do I turn the number 1 into 1 million? 2 bars on top of it. Are you with me? Okay. Now we're at the 492. How do I get 400? One piece at a time. 400. Which one is it? CD, right? Because C is 100, D is 500, so this would be 400. We'll get all the bars in a minute. That's 400. How do I get the 90? XC, we did that one a little bit ago, right? The 10 in front of the 100 gives me 90. And then how do I get 2? 2 I's. So this is the number after this one right here. This is the number 492. How do I get to be 492,000? I put 1 bar on top of it. The bars are almost acting like our parentheses, or not parentheses, our commas act, aren't they? I mean, it looks different, granted, but it's actually acting in a very similar fashion. And then I've got a 0, then I've got 19. Okay, so this is 19. I'm doing the 1, though, in the tens place first. How do I get the 10 and the 19? X. And then how do I get the 9 and the 19? IX. So in the Roman numbering system, it really is operating each individual number and finding its value. So in other words, I didn't write 19 as sort of like 1 and then 2 X's make 20, right? No, 21 is 1 here. They don't do that. It's just not their system. Okay? It sort of follows the same kind of an argument of how we think about their system, but that wasn't their system. So this would be how you would think about that. All right, and I meant to bring my actual physical blocks. I'll try and remember next time, but I didn't. There are base 10 manipulative blocks. Have you guys ever seen base 10 manipulative blocks? In any classrooms your base you've done or your Ruber from elementary school? I'll bring them next time, but let me kind of describe to you from a picture point of view on here what they look like. So a unit block looks like a little square. A long looks like a bunch of little squares all stuck together, so it's long. And usually when we're dealing with base 10, it's 10 long. That's kind of what we do. We see those. But it could represent any number long. It's just that we use base 10, so we see it that way. A flat actually looks like a 2-dimensional long. Looks like a very large square. Again, in the base 10 number system, you want to think about it being 10 long and 10 wide, whatever. So you get 100, right? On that block right there, a flat, rather, sorry, flat. And then a block actually looks like a 3-dimensional one of these guys. So you get the idea of it being sort of a volume concept, right? So you've got, and you can think about this too in terms of geometry, if you think geometrically. This is sort of the equivalent of a point. This would be the equivalent of a line. This would be equivalent of the XY coordinate plane, 2 space, 2 dimensions. And this is the equivalent of something like 3 dimensions when you're talking about volume. So these are different base 10 blocks. You're going to see some pictures in your book when they talk about base 10 blocks, and this is what they're going to draw them like. Their pictures are going to look good instead of being on slides like mine are. And so that's what they're talking about. But what you need to know is you need to know the language they're using. When they say long, you know what they're talking about. When they say block, you need to know what they're talking about. Okay? Now, a couple other things here is that you see this mentioned then as this having a power of 0, like 0 dimensions. This is a power of 1, which is a 1-dimensional kind of an object. This would be a power of 2. There are 2 dimensions, length and width here. And then this would be a power of 3. 3 dimensions, length, width, and height. Those kinds of ideas. All right, so I mentioned this idea of it doesn't have to be base 10. And the reason I did that is because we're not always going to be working in base 10. So I want to talk to you a little bit about other bases. And I've chosen just 3 kind of randomly. But what I first want to contend is that you use other bases sometimes and you may not be aware of it. So One of the base systems that is used, whether you use it or not, but a base system that is used is base 2. So maybe you know base 2 is used in what? In computer systems. Base 2, it's something called binary, is used for computer programming. Another computer programming base that's used is hexadecimal, which is base 16. So those are actually used in computer programming stuff. Do we know another base that you use? When you do time, you use a mixture of base 12 and base 60. It's not a real good example of one or the other, but it's a decent example of each one individually, right? So when you talk about the clock, you don't start over with seconds when you get to 10. You keep counting beyond 10 to 11 until you get to 59, but you would never say, for instance, it's 163, right? You start over once you get to 159 with 2 then. Same thing for the hours in the clock, right? We don't say that it's 13 o'clock, unless you're doing military time, and if you are, then you still don't say it's 26 o'clock. Okay, so we use some form of this when we do clock measurement. And you do it as well when you're using degree measurement, like in measuring degrees of circles, those kinds of things. You typically don't talk about an angle measure more than 360. People tend to start reverting back to what's called a reference angle and such. But, so we do use them in other places. Yes, Karen? In what way? It's not a different base because we have different measurement systems with temperature, but we don't see what bases do is they tell us when we start counting over again, right? So like, for instance, my son is still at the stage where he's learning to count higher numbers because he's still little. And last semester, actually, this happened, and he was counting. He was doing a very good job. He says 25, 26, 27, 28, 29, 2010. Okay? Which we, in some sense, is correct, right? That's what would come next, but we don't say that because that's the point when we round over. It's the point where we stop counting in that way and we count to the next decimal or the next place value system, base 10. So let's actually talk about our system. So ours is a base 10 numbering system, right? What are our numerals in base 10? Our individual numbers, what do we use? 0 through 9, right? We don't actually have a numeral that is a single digit that represents the number 10, yeah? The number 10 is actually represented by 2 digits, the number 1 and the number 0. We call it 10 and we're fine with that, but it's not a single numeral in our base system. And these other base systems have that same feature. So in base 3, there is no 3. In base 7, there is no 7. In base 12, there is no 12. Okay? Just like in base 10, there is no single digit to represent the number 10. There's something we call 10, but it isn't a single digit. So in base 3, just like in our base, we start with the number 0. And we have a base 10 system. We just said that it started with 0 and ends with 9, which means how many numerals do we have? 10. We have 10 numerals. So how many numerals do you suppose base 3 has? 3. What would they be? 0, 1, and 2. And then when we run out of digits in our system, when we hit 9, what do we do next? What do we do? We start again with, well, with 2 digits where the zeros in the ones place, right? So that's exactly what happens in base 3. When we get to the end of the 3 digits we have to turn it into a 2-digit number. Close. 1, 0. And we will read that as 1, 0. We will not read that as 10. There is no 10 in base 3. There is no 3 in base 3. But there are 1s and there are 0s. So we'll read this as 1, 0. And what will come after 1, 0? 1. Before that, 1, 1. And then 1, 2. And then I'm out of digits again, right? 2, 0. And we would keep going. You want to see? All right, so this would be 2, 1, and then 2, 2. Then what would happen? 1, 0, 0. Yeah. It's kind of like when we run out at the end of our numbers, 99. What happens after 99? 100. A 1 at the beginning and everything else turns into zeros. I can't go out as far because I won't have as much space, but base 7, what are the numerals in base 7? 0 through 6. And what would happen after 6? 1, 0. We start over until we get to 1, 6, and then I get 2, 0. Alright, I'm going to keep going from there. Base 12, though, is different. What's different about base 12 and 3 and 7? It's a 2-digit number in our system. It's actually bigger than our base system, right? If you're in base 12, you need more digits than you do in base 10. Just the way that base 7 needed more digits than base 3. So in base 12, you're going to have our digits up to 9. And then in essence, you need a digit for our number 10 and our number 11. And that's what you need. And I believe your book does T and E. Yeah, it does. I know it's different than the Contemporary Math book for those of you who've had it. T and E is what your book's going to use. T for 10, E for 11. Okay. So if you see those listed, that's what it's talking about. But at the point you get E, which is our number 11, you run out of symbols because you've already got 12 of them now listed from 0 to E. Okay. What would happen after the number E? 1, 0, just like with the other number systems. The difference comes in with, we'll get all the way up to 1, 9. What happens after 1, 9? 1T. Not space, but 1T. And then 1E. And then 2, 0. So you just continue past the 9 because we have more digits in the spaces. So we have T and E's. 1T and 1E. All right, so again, we're going to do just what we did in the last section. We're going to find the number before and the number after. It's just that we're doing a different base system instead of a different numeration system for different types of people. Okay? So the part A, the number preceding is the easier ones. We'll do that first. If you have the number 1, 4 in base 5, what comes before 1, 4? 1, 3. Sure. This should be 1, 3, and you need to write the 5, the word 5 down here beside it. And then 1, 4, 5 would come next. That's the one that's in the middle. And then I need to know the number afterwards. Okay, so 2, 0, right? So it can't be 1, 5 because why? There are no 5s in base 5, which means that the 4 is as high as you can go in the 1's place. So it needs to turn into a 0, and the 1 in the 10's place, in this case the 5's place, is the right of it. It needs to increase the left of it, whatever direction I was motioning. Oops. So the 4 becomes a 0, and the 1 here becomes a 2. So the number after it is the number 2, 0, base 5. T, 0, 0, base 12. The easiest one to do on this one is the one that comes after this. What comes after T, 0, 0? T, 0, 1. Right, you increase the last digit by 1. But anytime you try to take 1 away from nothing, which is in essence what we're about to do, that's the harder approach, right? So I've got T, 0, 0, and I want to go 1 back. So you kind of want to think about borrowing, yeah? So you want it to make it what? 9? E, E. So tell me why it's a 9. Let's start there. Why do we have 9? 1 less than T, okay? And then why do these zeros become E's? They're going backwards 1. It's kind of like if we had the number, let's say 600, right? So we borrow from the 6 and make it a 5. And the zeros would each become 9s, wouldn't they? The highest value in our place value system. Very good. So then this is base 12. Make sure you write the 12 down next to each of those. All right. Change the place system. All right, so we're going to convert from some base into a base 10 form. And as we're taking a look at base whatever into this form, we're going to do two things. The first thing we're going to do is we're going to put the numeral into expanded form. And the second thing we're going to do is we're going to multiply the expanded form out. All right, so let me show you what I mean by that. We're going to take this is in base 2. I've got a 1, I've got a 0, I've got a 1, and then I've got another 1 at the end. Each of those numbers are going to get multiplied by whatever base I'm in. So what base is this? This is base 2. Everybody with me? Okay. So this should be 2 to the 0. This would be 2 to the 1, 2 squared, and 2 cubed. That's actually expanded form of base 2. And I believe we've talked about expanded form of base 10, right? Have we? Or am I making your normal nodding, which means it may have been enough too. Okay, so in base 10 we have the ones place, and then we have the tens place, right? And then we have the hundreds place, and 100 is 10 squared. And then we have the thousands place, which is 10 cubed. They're all powers of 10 because we're in base 10. Well, in base 2, we have powers of 2. So we have 1 times 2 cubed, 0 times 2 squared, 1 times 2 to the 1, and 1 times 2 to the 0. So for a moment, let's just find out what these powers are. What is 2 cubed? 8. What is 2 squared? 4. And what is 2 to the first? 2. And what is 2 to the 0? 1. So these are all friendly because they're either being multiplied by 1s or 0s every time, right? So this is actually 8 plus 0 plus 2 plus 1, which is what? This is 11. And if it helps you to write it, you can write base 10 next to it just to remind yourself where you currently are, and you don't think that that has to be a base 2 because you've got a bunch of 1s in it. But you do not have to write the subscript word 10. If you don't write the subscript word 10, it's understood automatically to be base 10. Okay? All right, let's do the next one. We've got t, 0, 0. All right, so I need to take the number t times something plus the number 0 times something plus the number 0 times something. What values go in the empty blank parentheses that I left? Powers of base 12, because this is 12, okay? So this is really 12 to the 0, 12 to the 1, and 12 squared. What is the number t? 10. This here is the number 10. What is 12 squared? 144. 12 to the first is 12. And what is 12 to the 0? 1. So the only one here that I actually have to do any multiplication for really is 10 times 144, which is 1,440. This is multiplication. So anytime, this is one of those things that probably is going to go on a note card to remind yourself, maybe not for everybody, but for many of you. Anytime you're taking some other base, whether it's smaller than ours or bigger than ours, and turning it into base 10, you're multiplying. Always. You're always multiplying to turn something into base 10. So what do you suppose is going to happen if you take something in base 10 and turn it into something else? All right. Computer's not cooperating. This is going to be turning base 10 into something else. All right? Consider the expanded form for the base, which we'll talk about, and then we're going to use the division scaffold. And the division scaffold is a wonderful tool that your book uses, and the contemporary math book, for those of you who've taken it, it doesn't do this. But once I saw that this book showed this method, I thought it was so wonderful. I'm putting it in that class now because it works so much nicer. So if you've taken contemporary math, you probably haven't seen this even so. All right, so you may have last semester, I don't know, depending on if you had me or not. All right, so the first thing we're taking a look at on this one is we're turning this into base 4. So what we have to do first is we have to consider the expanded form for the base. So what in the rule does that mean? Well, it means I need to look at what the powers of 4 are. And that's what it really means. I need to know what are my powers of 4. So obviously, I know I'm starting with, it's always 1, because 4 to the 0 is 1. Right? And you can grab your calculator as you're looking at these. The next one's going to be 4. After you do that, you're going to have 4 squared. So, somebody's going to grab a calculator. What's 4 squared? 16. 4 cubed. 64. And 4 to the 4th. 256. And from here, if you want, you don't have to keep doing powers of 4. This is actually a sequence. What kind of sequence is this? It's geometric sequence. The way you get to the next term is by multiplying by 4, because it's base 4. So 256, what's 256 times 4? Yep, 1024. And then times it by 4 again.
4,096.
Good. And one more time. Okay, and then I contend that we've gone far enough, and here's how you know. You've gone far enough when the number you get, the last number that you got, was bigger than the number you're supposed to be working with. Okay? So I don't need to go past 4,000 because 16,000 was larger than the 11,000 I'm starting with. I don't need that. But I do need everything else. Okay? You ready to see how this works? All right, so what we're going to do is we're going to take the large number that we started with, the 11,028, and we're going to divide it by the largest base 4 number that goes into it, which is 4096. So it kind of looks like division with this extra area over here, doesn't it? And what we're going to ask ourselves is, or you're going to ask your calculator to do for you, is how many times does 4096 go into 11,028? Somebody tell me. 2 times. You're going to put the 2 over here on the right-hand side. And then you're going to take your calculator and you multiply the 2 on the right-hand side times the 4096 on the left-hand side, which is what you would do in long division. This is long division so far. It just has a different thing that I'm putting on the right instead on top. So what is 2? So normally you're used to seeing this. You're getting, it looks like you know what long division is. This is 2. 2 times 4096. What's 2 times 4096? Okay? Now, I'm putting it back where it goes. Over here. So far, so good? Subtract. This is what you do with long division. What's 1,128 minus 8,192? Or, I'm sorry, 11,028. I said it wrong. 2,836. All right. And that number should be smaller than that 4096 you divided by already. And it is, so we're in good shape. The next thing we do is we use the next power of 4, 1024. You let your calculator do it again. How many times will 1024 go into 2836? You should know that one. 2. 2 times 1024 is what? $2,048. 2,048. And we'll subtract. What is 2836 minus 2,048? 788? Excellent. All right. Now I'm at 256. How many times does 256 go into 788? 3 times? Okay. What is 3 times 256? 768. And if I subtract, what do I get? 20. Now here's where you don't want to be tempted to do something inappropriate. you need to write down the next power of 4, which is 64. I get it, it's too big, right? Which means it goes in how many times? 0. But you need this 0 right here. If you don't put that 0 in, you're going to have an error in your answer. Okay, so it's 0, and 0 times 64 is 0, and that's fabulous, and I can still write down 20, and I'm happy to do so. I'll multiply by 0 anytime you ask me to, that's fine. It's always easy, right? Okay, so I've got 20. My next power is 16. So how many times does 16 go into 20? 1. 1 times 16, 16. And I subtract and I get 4, which is my next value here, 4. 4 goes into 4 how many times? Once. 1 times 4 is 4, and I subtract and I get 0. Again, I need to do it until I get to the very end of my powers of 4, and my last power of 4 is 1. And 1 goes into 0 how many times? 0. And then, of course, technically we would be finished at that point. So you might say, okay, fine, there are a lot of funny divisions and some of the things were zeros, and that was really weird, but here's the cool thing. This is your answer. 2, 2, 3, 0, 1, 1, 0, base 4. That is your answer. And you can read it straight off the scaffold, which is pretty cool. Any questions on that one? We're going to do one more of these, okay? At least in theory, if I can get my board switch. Okay. We're going to convert from base 10. Number is 99,999, and we're going to put it into base 9. Okay? So I need to know, the first thing I need to know is what are the powers of 9? And I'll get you started. 1, 9, 81. The powers of 9 that I have in my memory. What's the next one? And you can get there by multiplying by 9. This is a geometric series. So what comes after 81? 729, okay. Then what? 6,561. Okay. Look like that? Okay, go one more. And while I could have you go one more, you have to know that's enough, right? That's 59,000, and the number I'm supposed to be working with is 99,000, which is about double, right? Not even quite double. I definitely don't need to multiply 59,000 by 9 and figure out what the next one is. It's going to be too much. So, as I do my division scaffolding, this 59,049 goes on the outside. And I want to divide 99,999 underneath. And it's going to go in how many times? Once. 59,049. And I'm going to subtract. What am I going to get? 40,000, what's next? 950. Awesome. So I've done my first power, largest power, of 9. And the next one I need to do is 6,561. So, using your calculator, how many times will 6,561 go into 40,950? 6. What is 6,561 times 6? Awesome. But I need to subtract now, yeah? 40,950 minus 39,366. It's what? Remember this one now. 1,584. What will I divide by next? 729. How many times will 729 go into 1,584? 2. 2 times 729 is what? 1458. If you subtract, what do you get? 126. What will I divide by next? 81. How many times will 81 go to 126? Once, right? What's 126 minus 81? 45. Now what am I dividing by? 9. How many times will 9 go into 45? 5. Oh, it's like in chorus. And 5 times 94. Sorry, 5 times 9 is 45. Do not be tempted to stop early. This is a remainder of 0 at the moment. However, I gotta finish. I gotta do the division by 1. It doesn't always end up happening that the part at the end looks silly. Okay, it doesn't always. But this goes in, of course, 0 times, and then you're finished because you've used all your powers of 9. So all the powers of 9 over here on the left-hand side, and your solution is on the right-hand side. So what is your solution here? Base 9. Make sure you have that subscript word 9 on the bottom because otherwise it's understood to be base 10. It matters. All right, so here's what we're going to do. I'll only stop the recording for a sec.